In this video, we are going to apply the node voltage method to a circuit containing a dependent source. In this circuit component is an ideal independent voltage source, and this circuit component highlighted in green here is a dependent source. We can see that inside the symbol we have a plus minus sign, so this indicates that this component is a dependent voltage source, and we can see that its magnitude is in terms of a current I phi. So this means that this circuit component is a current control voltage source. So let's apply node voltage method to this circuit. The first step is to identify essential nodes. In this circuit, we have 1, 2, and 3 essential nodes. Recall that an essential node is a point in a circuit where 3 or more circuit elements meet. The next step is to make one of these essential nodes a reference node. So we can make this bottom essential node a reference node and we ground it. Next, we need to apply Kirchhoff current law to the remaining nodes. So let's label the node voltages as V1 and V2. A systematic way of applying Kirchhoff current law to these nodes is to assume that we have all branch currents flowing away from the node. So in this case, we have 3 branch currents at node 1, and we have another 3 branch currents at node 2. Now we are ready to apply Kirchhoff current law at node 1. First, looking at this branch current. So we follow the direction of this branch current. And apply Ohm's law to this resistor. So we have voltage on this side minus voltage on this side divided by resistance. The voltage at this side is 20 volts because we have the ideal independent voltage source directly connected between this point and ground in the circuit. So that means this branch current is given by V1 minus 20 over 2. The next branch current is through the 20 ohm resistor, and this is given by V1 minus 0 over 20. And then the last branch current is through the 5 ohm resistor, and this is given by V1 minus V2 over 5 is equal to 0. We repeat the process at node 2. So this branch current through the 5 ohm resistor is now given by voltage at this side minus voltage at this side divided by resistance. So this is equal to V2 minus V1 over 5. The branch current through the 10 ohm resistor is given by V2 minus 0 over 10. And this last branch current is obtained by using Ohm's law. So we follow the direction of this branch current. The end where this current is entering the resistor is assumed to be at higher potential, and the end where it is leaving is assumed to be lower potential. Hence, this branch current is V2 minus 8 I phi over 2. So what we get is V2 minus 8 I phi over 2, and this is equal to 0. The last step is to write the dependent source constraint equation. The dependent source constraint equation means we need to write the controlling variable I phi and express that in terms of the node voltages V1 and V2. The direction of I phi is given, so we need to apply Ohm's law to the 5 ohm resistor, and we can write the dependent source constraint equation as I phi is V1 minus V2 over 5. Hence, we have three circuit equations and three unknown variables, V1, V2, and I phi, and we can solve these equations to get the solution. We can easily use Mathematica to solve these equations, and using the solve command in Mathematica, the solution can be obtained as shown here. Hence, the obtained solution is V1 is 16 volts, V2 is 10 volts, and I phi is 1.2 amps. Now we can solve for the circuit variables, and in this case we have to find the power associated with the dependent source. So what we need to do is, power is given by the product of the voltage and the current. So let's assign the current through this dependent source as Ix, and this current Ix can be given by V2 minus 8 I phi over 2. And if we substitute the values, this gives 10 minus 8 times 1.2 over 2. So this is equal to 0.2 amps. Now the power associated with the current control voltage source is the product of the voltage, which is 8 I phi, and the current, which is Ix. We apply passive sign convention to decide the sign of the power equation. Since this current Ix is entering the terminal marked plus, we use the power calculation with a plus sign. Now we can substitute values to get the result. So this is equal to 8 times 1.2 times 0.2. So this is equal to plus 1.92 watts. So this positive answer means that the current control voltage source is dissipating power in this circuit. We can use PSPICE to confirm our solution. In PSPICE, the current control voltage source is available as part name H poly. And please note the way the circuit element is connected to make sure that it is configured properly. So we can simulate this circuit, and then we can see that the node voltages are 16 and 10 volts as we calculated, and the current is 0.2 amps I phi, the controlling current, which is exactly as we calculated. We can also simulate the circuit in LTSPICE. In LTSPICE, the current control voltage source is available with part name H. In order to properly configure this part, we need to connect a voltage source V0 having 0 magnitude in the path where the controlling current is, and then we can configure this current control voltage source as indicated here, where 8 is the coefficient, the gain, and this tells LTSPICE where to find the controlling current. So this way, by connecting a 0 volt test source in series with the path where the controlling current is, we can simulate this circuit, and this 0 volt voltage source does not change any of the circuit current or voltage values. So when we run this simulation, PSPICE gives the DC operating point, and rather than interpreting these results, we just need to hover the cursor over the part name of interest. So in this case, when I hover the cursor over the current control voltage source, in the bottom left corner, we can see that the power dissipated is 1.92 watts as we calculated, and the node voltages are 16 volts and 10 volts. So this confirms the solution.